Usually does update a little bit, but
These guys fail.
now that we figured that out,
That's why it shows histories, because I know.
those of you who
a lot of these classes
don't want to watch the last logic course, now that we know what we're doing, you're free to leave at any point, or you can just bask in the glory that is axiomatic set theory. It's beautiful. For the rest of you, let's quickly recap and get back to where we were when we left off on set theory. So axioms of set theory, just try and go fast, but if you need me to slow up for one, let me know. So axiom 1, the first one was that X is a member of Y. That is a proposition if and only if X and Y are sets. Remember, what are our two undefined terms in set theory?
In and set.
Yeah, that is a member of symbol and set. Those are our only undefined terms. Everything else is defined in terms of these things. Now, X and Y is a proposition. What's a proposition?
It's a statement as true or false.
Something that's true or false, not both. That is a proposition if and only if X and Y are not sets, or if are sets. And remind you of why this axiom is so necessary. Go back to Russell's paradox. What was Russell's paradox? He said, let's look at the set U. And what is the set U? It's a set of all sets that don't contain themselves. It's a set of all sets that don't contain themselves. So if X does not contain X, that implies X is in U. If X does contain itself, that implies X is not in U. Right?
Yeah.
Now the question is U in U? Does a set of all sets that don't contain themselves contain itself?
No.
Well, the question is, let's say U does contain itself. If U contains itself, but U's a set of all sets that don't contain themselves, then U doesn't contain itself. So if it doesn't, it doesn't. So it must not contain itself.
But if it doesn't.
So U does not contain itself. But U is a set of all sets that don't contain themselves. So U contains itself.
There is no true or false.
So the answer is, U's not a set. You can't just go around calling things sets willy-nilly. You don't get to decide what a set is. A set is a set. It would be like me saying, let's look at the prime number 4. No, it's not a prime number. I don't just get to make it so by calling it a prime number. Or one that we've come across in logic already, I say, this statement is false. Is that statement true or false?
It's not a statement.
It's not a statement. I don't get to define statements into existence. So, that was our first axiom. Now that we've introduced those symbols, we had a bunch of definitions. First off, what does it mean for X to not be a member of Y? It means it is not the case that X is in Y. Okay, straightforward. What does it mean for X to be a subset of Y? It means for all A, if A is in X, then A is in Y. Everything that's in X is also in Y. That's what it means for X to be a subset of Y. X is equal to Y means that everything that's in X is in Y, and everything that's in Y is in X. Now, warning, we're defining equals. Isn't equals a symbol of logic? How do we justify that?
We're adding more definition to it.
Yes. So, yes, equals is a concept of logic, and we are extending the definition is the way it's often expressed. We're extending the notion. We're extending what we mean by equality inside of set theory. So equals still means everything that meant in logic, and now we're extending the notion a little bit. And then finally, what does it mean for X to be a proper subset of Y? It means X is a subset of Y, but X is not equal to Y. So everything that's in X is in Y, but there are still things in Y that are not in X. Y is for sure somehow bigger than X. Good so far with that? Quick recap.
Yes.
Our second axiom was simply that there is an empty set. And then the first theorem we proved is that the empty set is unique. So this gave us that there is at least one empty set. We proved, and there's only one empty set. And so since there's one and only one empty set, we can now define it with that symbol. And that symbol is now well defined because we proved it's unique. Axiom 3, if X and Y are sets, then there exists a set, curly brace, X comma Y, end curly brace. There exists a set whose members are exactly the sets X and Y. Then our next theorem was that the set containing X and Y is equal to the set containing Y and X. Intuitively, how did we prove that? We showed that this is a subset of that and that's a subset of that. So they're equal to each other. Because that's how we extended our notion of set equality. And now this gives us our notion that order doesn't matter in a set. And then next we defined a singleton set. What does it mean to have the set containing just X? we define that to mean the set containing x comma x. Because so far, this was the only notation we had defined for writing out a set. And so we had to define this notation using this notation. And so that's how we did it. And this gives us our notion that duplicates don't matter in a set. So order doesn't matter in a set, and duplicates don't matter in a set. Doesn't change the set. Good so far? Okay. And then we quickly gave our set theoretical definition to an ordered pair. Remember, an ordered pair now, order does matter. And so the ordered pair, 1, 2, is very different from the ordered pair 2, 1. And so the set theoretical definition, because remember, now that we got set theory, everything is sets inside sets inside sets inside sets. It sets all the way down. It's turtle all the way down, right? Sets all the way down. And so it's just sets inside sets inside sets. That's all it is. Jumping the gun to give you some weird intuition for this, here is 4 written out explicitly. Sets aside, sets aside, sets aside, sets aside, sets. That's all it is. A bunch of sets. Every mathematical object that we work with, we can give it its set theoretical definition.
We never got to that last week.
I know. That's why I'm going to try and hurry up and finish off.
Okay.
But don't want to go so fast I lose you. But fast enough that we can quickly recover to where we were, since it's been a little bit since we met. So now, this order pair, here's its definition in terms of sets, and that now tracks order. When I look at this, I can always figure out exactly which element came first and which one came second when I look at that set. And I check, is this inside this set or is this set inside this? Whichever one is inside the other is the one that came first. Make sense? Okay. And then we can now define an ordered triple. An ordered triple is really just a special order pair. It's an order pair where the left-hand element also happens to be an order pair. And now we can define a 4 tuple and a 5 tuple and a 6 tuple similarly. And so n tuple, a list of n elements, is defined as the ordered pair where the left-hand one has n minus 1 elements and then your nth element is there. So it's a recursive definition. Good so far? All right. So axiom 4 then is if x is a set of sets. Now all sets are sets of sets, but I just want you to keep in mind it's a set of sets, and we're going to think about the sets inside of x. If x is a set of sets, so the things inside of x are more sets. If x is a set of sets, then there must exist some other set m such that the elements of m are the elements of x. And we write that m is equal to the union of x. This is now just scribble stuff. So let me draw out a picture to give you the feel-goods. Here would be an example of a set x. X is a set containing the sets A1, A2, A3. Okay, there's a set inside of x. Here's x. When I union up this set, that means this set union together with this set, union together with this set. Now we haven't defined that notation. That was just me giving you the feel-goods for what's talking about. That make sense so far? Okay. Now, we know that when we're writing out sets, we use this curly brace notation, and we list out our elements, comma separated, then put an ending curly brace. Right now, we're only allowed to do that with 1 element and 2 element lists. So now, let's extend our definition now to more than that. So now, what does it mean when I write out this 3 element set, A, B, and C? By definition, it is the union of the 2 element set, A and B, together with the 1 element, C. Keep in mind, that set is now perfectly defined notation from over here. That set is now perfectly well-defined notation from over here. And now, the unioning of sets is something that was given to us in Axiom 4. So we're all well-defined now.
Yep.
And so now a 3-element set is perfectly well-defined in terms of a 2 and a 1-element set. And now you can extend this notion further and define a 4-element set as a union of a 3-element set together with a 1-element set. And you can describe a 5-element set as a union together of a 4-element set with a 1-element set. And in general, you can define an n-element set as the union of an n-1 element set together with a 1-element set. You with me so far?
Yeah.
Okay.
Does that imply that sets generally only have 2 elements in them, and that they're just kind of just a bunch of 2-element sets combined together to make multi-element sets?
Well, what we did is we took 2-element sets that one axiom gave us, and the union that another axiom gave us, and use that to construct as many element sets as we wanted.
Yeah.
So now we can write out any finite set.
But he's asking if like, well, if
Like
it comes
by
down.
definition, they're really.
It's not the same as this. This is always defined in terms of an ordered pair.
Yes,
This one is not.
it's unordered.
This is now, well, it's not just unordered. We don't notice that a 3-element list is really just a 2-element list.
Which has a set here.
A 3-element set is not really just a 2-element set.
Oh, okay, that's what I was asking.
Okay, so I think we got your question. It's just the union of that set with that set gives you this set. And so we're using the union operator to define larger than 2-element sets.
That does seem awfully similar to the other definition, but I'll
There's a similar element to it, but when we look at its actual definition, it's something different. This set is the union of an n-1 element. An 8-element set is defined as a 7-element set, union together with a 1-element set.
Oh.
Up here, an n-element list is really just an ordered pair, where one of the ordered pairs happen to be an n-1 element list.
Okay.
And so this one is just a bunch of nested ordered pairs. Okay. Good with everything up till now? Again, this is just review.
Yeah,
So I'm
and
going fast.
We're just really deep into this, so we're right with you.
Yeah.
Topology drilled this into us hard.
Unions and stuff.
That's great. Okay.
Flashbacks, bro.
So next, definition of a functional relation. First off, what's a relation?
It's a two-term predicate.
It's a 2-term predicate. What's a predicate?
It's something that returns. Wait.
It takes terms
And returns true or false.
and spits out true or false. An operator takes terms, spits out terms. A predicate takes terms, spits out true or false. So a relation is a 2-term predicate. And now we have the notion of a functional relation. What's a functional relation? And it's already the intuition you have. What's a function?
It's a set of order pairs.
With, what's the property a function has?
One input.
Every input has a unique output.
Yeah.
That's all that this is saying. A relation R is functional if and only if, for every x, there exists one and only one y, such that x is related to y. Every x is related to one and only one y. We use this notation when our relation is functional, a lot of the times. If x is related to y under relation R, where R is a functional relation, we say y is equal to R of x.
Can we just call it a function? Why do you have to say a functional relation?
We just need to be careful about what we are calling to mind when we use a word. Because we are not using a set theoretical function yet. Because a set theoretical function, which is what 99% of people mean when they say the word function, is defined in terms of a set theoretical relation, which we have not defined that either. Because we're still working with sets. Once you get set theory, then you do a set of ordered pairs as your relation, and then you do a function in the sense that you know and love. And it just keeps creating a more and more restricted notion. So we've already had a notion of a function in logic.
Yeah.
And then this is now a more restricted notion of what we mean by a function. And then we'll get a set theoretical function, and this is what is always meant from there on out by the word function.
Gotcha.
But it's always just a more restricted notion, so everything that's true about your set theoretical function is also true about this type of function. But the converse cannot be said to be true because,
Obviously.
yeah, the other fields haven't even been developed yet.
Yeah.
Right. So, functional relation. Almost what you would have guessed. Okay, so next axiom, axiom 5. This is the one that gives us our set builder notation that we want so desperately. And so axiom 5, it's a very, it's surprising that it gives a set builder notation, but it does. So let M be a set and R a functional relation. Then the image of R under M is a set. In other words, if I take my set M and I run it through R to get all the outputs, the collection of all those outputs is also a set, is what this says. So take a set of inputs, run it through a functional relation, the set of all outputs that come out is in fact a set.
The set of all outputs.
The collection of all outputs that comes out is in fact a set.
Okay.
The outputs that come out constitute a set.
One into a range.
Sorry, what?
Is it an image?
The image. The image of
Yeah.
R under M is how you read that.
Like range,
Oh.
image, domain.
Range and image mean the exact same thing.
Yep.
It's just everyone says image when it's a more advanced class, and range for some reason caught on for
I thought
lower
the range was
classes.
the input and the image was the output or whatever.
Domain is
Domain's the input.
Oh, that's right.
Range is the output.
Okay.
So range and image, exact same thing.
Yeah, I'm with you now.
Okay. So there is that. And now we're going to recap on theorem 3. I told you that this is going to be the hardest part of covering the little bit that we're going to cover. And it's the theorem that gives us set builder notation. Now what we want from our set builder notation is I want to be able to take all the elements of a set that satisfy some condition. So if I were, for example, talking about all the even integers, what would all the even integers be? We'll use capital E to mean evens. I would want to say that this is equal to the set of all
the numbers that
n in z, all the integers, such that 2, you might not be used to the symbol, it just means divides n. Just means 2 goes into n evenly. So that's a way that we could represent all the evens if we had this set builder notation.
Yeah.
And closing bracket there. So this theorem is the one that is going to validate our set builder notation for us. Now think about what this set would be. Think about a mechanical process for generating the set of evens. What would I do? I would iterate over all the integers and I check, are you even? If you're even, I stick you in my set. If you're odd, I throw you over the wall. Right? And through that process, we select everything out of there that's even. So that's what we're going to get with this. We'll think about this predicate here as being the is even predicate, and our m here as being the integers for the sake of an example as we go through the theorem. Again, we went through this last time, but it's one that's a bit hard to follow the first time you come across it. So let p of x be any predicate, like the is even predicate. Or the is divisible by 2 predicate. 2 divides it predicate. So p is we'll think about as an is even predicate. Let p of x be a predicate, and m any set. We'll think about m like the integers as an example. Then the elements y in m such that y satisfies p. So the set, the elements y in the integers such that y is even, is a concrete example, constitutes a set. That's what we need to prove. And we're going to denote that set as a set of all y in m such that y satisfies some predicate. Or the set of all n in z such that n satisfies some predicate. We can think about the 2 divides it as a predicate. To be a bit pedantic here, I could have said my p of x here is 2 divides x, and then I could have put p of n right here just to try and follow the same notation. If this is my p of x predicate, then here's our evens. It's a set of all n and z such that p of n. What's p of n? Well, that's the 2 divides it predicate. Good? Okay. So, we need to prove that taking all the elements out of a set that satisfies some predicate, the result is in fact a set. And then we will denote that set using this set builder notation. It's a set of all the y from this set M that we ended up choosing with our predicate. Our predicate here is acting like a filter, picking out the elements we want.
Yeah.
Okay, so 1. Observe that either there is something in M that satisfies P, call it Z. Observe that either there exists some Z in M such that Z satisfies the predicate P, or there is no such Z in M that satisfies the predicate. So pick my filter on my set. Either something in the set satisfies a filter, or nothing in the set satisfies a filter. Has to be one of those 2 things. So if there is no such Z, if there's nothing in the set that the filter satisfies, then we define the set builder notation to be the empty set. In the special case where there was no y in M such that p of y was true. And that's the empty set.
Is that a definition or is that?
Yeah, it's what we're going to mean by this notation, because this notation signifies all the y in M that satisfy the predicate.
Oh, okay.
We're kind of defining what we're going to mean by this notation right here.
Yeah.
So by this notation, I mean all the y in M that satisfy p of y, and I need to prove that it is in fact a set. And we're just fine calling it set. Okay, so we handled the case where there is nothing. There is no such v in m such that our filter satisfies it. It would be like if I scanned the integers for all the multiples of pi. There are no multiples of pi in the integers.
Yeah.
Pi is an irrational number, 3.14159, da, 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 da. No multiple of pi gives you an integer. Okay. Now, if there does exist some z in the integers, such that z satisfies p, then we're going to define some functional relation. We're going to define a clever functional relation such that its image is all the members of M that satisfy P. And we know that the image of a functional relation is a set. So I may be clever by coming up with some functional relation whose image is precisely the members of M that satisfy the predicate P. Okay? When I define this functional relation, what do I know so far? I know there is some z out there that satisfies the predicate. In our concrete case, if we're thinking about our predicate as the 2 divides it, or the is even predicate, and we're thinking about our m as being the integers, our z here could be something like the number 28. Something out there that is for sure even. Something out there that for sure satisfies our predicate. Doesn't matter what, just something. With me so far? So now, how do we define our relational predicate? Or our functional relation? We define it like this. X is related to y if and only if x satisfies our predicate, x was even, and x and y were the exact same thing, or x did not satisfy our predicate, and y was 28. So we map x to y, we map x to itself anytime x is even, or satisfies a predicate, and we map x to 28, or we map x to z, anytime x was not even, or didn't satisfy the predicate. Now it's hard for us to consume it like this. Here it is using functional notation that you're more comfortable with. Understand we have not defined this notation, this is just for the fill-goods. What is R doing? R takes some x, it checks. Does x satisfy p? Then it maps it to x. If x does not satisfy p, then it maps it to z. Or in our concrete case, is checking what is r of x. It's equal to, if 2 divides x, then we're mapping it to x. If 2 does not divide x, then we're mapping it to 28. You with me? So what does 0 pair to using this function? 0 is even.
Oh, it is. You're right.
Yeah. So what does 0 go to?
It would be x, right?
0's not even.
Can you find an integer such that 2 times that integer a equals 0?
Yeah, 0.
0. So if you can find an integer such that 2 times an integer gives you your number's even. Definition of even.
Yeah, accurate.
Yeah, 0's for sure even. Okay.
It's not like divisible by 2 though.
Is the definition of odd just not even?
Now, that is not the definition of odd. The definition of odd is a number is odd, a number m is odd, if and only if there exists some k such that m is equal to 2 times k plus 1, where k is an integer. It's even if it can be expressed this way. It's odd if it can be expressed this way.
Because it only works.
Right now.
And so it's a proof to show that every integer is either even or odd. That's something you prove.
Not all numbers. Not all numbers.
But is 2 divisible by 0?
No,
So,
nothing's divisible by 0, and 0 is divisible by everything.
2 divided by 2.
so how could, using our predicate there, how
0 divides x is always false. X divides 0 is always true.
Oh, okay. Wait. Okay.
What?
0 divides x is always false. X divides 0 is always true.
You might divide like
Unless you put 0. In the special case where x is 0, okay, 0 divides itself. Because every integer divides itself.
you should start writing division like
Oh,
It's not division, it's a predicate, it means divides. It's not division. It's not an operation, it's a relation.
So 3 over 0 works.
No, this
So the right one doesn't work.
No, he's saying 0, 3.
x divides 0 is true. This is not x divided by 0. This is a relation, it spits out true or false. This is an operation, it spits out a number.
That's right. Opposite.
Two very different things. Just similar names. Divides versus divides you can think about like is a factor of.
Yeah.
0 is a factor of x? No. X is a factor of 0? Sure.
Doesn't that?
This is the first time I've heard of this operator. Or function, or, okay. Or
So
relation.
that means that.
But you do something logically equivalent in programming all the time. When you do x mod 2 equals 0, that is logically equivalent to saying 2 divides x.
Yeah.
So use the concept left and right. You
Use it a
just
lot, I've just never seen
don't
it.
use that type of notation. And there's probably tons of libraries you can use that have built-in divides that you can
Oh, I've used a million.
plug on the
times.
number.
That particular symbol could be piping, it could be or statements, it could be,
Anyways, quite the contrast. Okay, so let's think about this function now, operating on the integers. If I plug 0 into it, is 0 even?
Yes.
Yes. So 0 maps to
South.
0. What does 1 map to?
28.
28. What does 2 map to?
28. Or sorry, 0.
2.
2. What does 3 map to?
28.
What does 4 map to?
4.
What does 5 map to?
28.
What does 6 map to?
6.
So you're noticing everything that satisfies the filter, we're just mapping to itself. And everything that doesn't satisfy the filter, we're just mapping to something that did. And so all our outputs, notice, are going to be just the evens. So all our outputs are just going to be the things that satisfy P. If X satisfies P, we're outputting X. If X doesn't satisfy P, we're outputting Z. What was Z? Some random thing that for sure satisfied P. Did I say satisfies X? I'm not sure if I said that wrong, but I think you understood me right.
Yeah.
Yeah, I follow.
Okay. So, there we go. We've defined some functional relation, and we've defined it in this clever way where all the outputs, the image of this function, is only going to be things that satisfy P. So, if x is related to y, and x satisfied P, then what must y have been? If x is related to y, and x satisfied P, what does y have to be?
Something that satisfies P.
When I plug in an x that satisfies P, what does it output?
X. So it has to be
X. So what does my output have to be
X.
if we satisfy the predicate? My output y had to be x. So if x is related to y, and x satisfied P, y had to be x. And so I now know that y is something in M, and y satisfied P. On the other hand, if x was related to y, and x did not satisfy P, what does y have to be? Z. And Z for sure is something that satisfies P. So y is in M, and it satisfies P. So the image of our function is precisely the set of all y in M that satisfy P. And so, the set of all y in M such that the collection of all y in M such that y satisfies P turns out to be the image of this thing, and so we're justified in calling it a set. Because Axiom 5 says that the image of any functional relation is a set. It's a lot of work, but once you see it, it seems clear as day.
Yeah, it makes sense. Yeah.
And the whole crux of the proof is just coming up with that clever relation. But now we have our set builder notation, which we will fall in love with. Any questions before I move? Oh, we didn't finish all this, did we?
There's one more definition at the bottom.
Yeah.
So, yeah, don't let me skip any definitions. Okay, so now we're ready for some definitions. What is the intersection on X? Intersecting all the sets inside of X together. It's defined to be all the A from some set. Notice that we always have to specify what set we're filtering on when we use set builder notation. Why do we have to specify the set that we're filtering on?
Because then if you don't, you'll get
We can get back to Russell's paradox. I could say let U equal, what would it be? It would be the set of all X such that X does not contain X.
Does it give you like a free variable? Or like not a, going back to logic?
No, it just makes I don't know that the things I'm selecting from actually come from a set.
Actually.
Over here, we're always forcing our selections to already belong to some set. In other words, this is somehow getting at a collection that is too large, maybe not this one exactly, but there's a lot of collections out there that are too big to be sets. And so this stops us from accidentally taking something that's too big to be a set and calling it a set. Because we're only filtering from things that we already know are sets.
What the heck is too big? Like infinity?
No.
Do we dare talk about ordinals?
You can still have infinite sets.
So an ordinal, the set of ordinals are what we call, okay, I'll tell you, the set of all ordinals. What are the set of all ordinals? We go 0, 1, 2, 3, ... And we go all the way up. Oh, this won't make sense. It'll make sense after we cover what's at the end there. I'll jump the gun, force me to come back to this.
Great.
But we'll get up to something that I may call omega, which is basically infinity.
Yeah, it's past it.
And then we go to infinity plus 1, infinity plus 2, and we go on our merry way.
That seems like it breaks the laws of.
It seems like it breaks some stuff. And the set of all these things is continuing on its merry way is not a set, the collection. It's what we call a proper class. And it's beyond, that's getting into advanced math, working with infinities that we are not prepared for.
Wait, why is that not a set?
Because it's not.
You call it proper class?
Yes, that one's called a proper class.
So proper class.
The collection of all ordinals is what you would call a proper class.
What about that does not make a set?
What goes
That
beyond
will
proper
enable
class?
you to get into paradoxes.
How?
We will not derive a paradox from the ordinals. You'll just have to take my word for it or research it on the side. It's getting advanced. Talking about these infinities, we're not close to ready for it yet. Before we even did that, you'd have to get comfortable with what we call the axiom of choice, and that's already a tough one to get comfortable
That
with.
one is, yeah.
So, sorry.
Oh, are we talking about diagonalization today?
We could probably talk about that. It's a good thing to talk about before you talk about ordinals. Okay. Anyways. So this forces us to only select things that for sure could fit in a set.
Gotcha.
It's a set of all the elements from some other set that satisfies some condition. And now notice that the union on X is something that we know is for sure a set simply from Axiom. Where did we get it? 4. So this is, what is the intersection of all X? Well, we're going to take everything that would have showed up in X's union. What's X's union? It's everything that showed up in any of the sets. What do we want in the intersection? We want all the A's that showed up in all the sets in X.
Yeah.
So A is in our intersection if and only if we take all the things from the union, and we select it if and only if for every B in X, A showed up in B. So A had to show up in all the sets in X. That's the only way it shows up in the intersection. Let's write a concrete case. X could have been equal to the set containing the set 1, 2, comma, 2, 3. 2, 4. I should never try to write 3's when I'm writing brackets. Okay. Then what is the intersection on X? It is a set of all X in the union. First off, what's the union on that?
It's a set of 1, 2, 3.
The union on that is just 1, 2, 3, 4.
Where's the 3?
1, 2, 4. Thank you. Okay, there's the union on it. So now we're selecting out of here all the things that satisfy this condition. What's this condition? For every B in X, for every set that shows up in X, so for this set and this set, A has to show up in there. So for this set, let's see, does 1 show up in here? Yep. Does 1 show up in here? No, so it does not show up in our intersection. 2, does 2 show up in here? Does it show up in here? So 2 does show up in our intersection. And then 4 does not. So in that concrete case, there it is.
But the empty set also shows up in both, right? So
The empty set, what?
you should.
The empty set is not in here, and the empty set is not in here.
But when we're taking an intersection of 2 sets that are disjoint, the intersection is an empty set.
For 2 disjoint sets, yes.
So
So an
doesn't that-
intersection can produce the empty set.
Doesn't that imply that the empty set is in both sets?
Implies nothing's in both. It's what's in the empty set that shows up. It's what's in the set. The members of the set show up in everything.
So it starts out with
Here's the empty set.
It still does.
Yeah.
Here's everything in the empty set.
Yeah.
Okay. So easy to get confused back and forth
Okay,
between
we-
talking about nothing and the empty set.
When we're taking the intersection between two disjoint sets, how do we get the intersection? How does that come out?
All right, let's do it. So I want to do the intersection on the set containing the set 1, 2, 3, 4.
Yeah.
Okay, this is equal to the set of everything that shows up in both those sets.
Okay. So that's not. But that kind of feels like it should imply that the empty set was in A and B.
No, it's saying everything inside the empty set was an A and B. Pick anything you want in there, and it shows up in both these sets.
Oh. Okay.
Vacuously true.
No, I see. Okay, I see.
Okay, any other questions?
Now it's really confusing.
Yes, it is. Until you just get used to it.
Yeah.
Yes, that's how it always goes. All right. Good enough. Don't let me go to the whiteboard. Okay. Axiom 6. Let M be a set, then there exists a set denoted the power set of M, whose elements are all the subsets of M.
Yep. That's your.
So if there's a set out there, then there's a set of all its possible subsets. Using the set builder notation you know and love, the power set of M is a set of all X where X is a subset of M.
Is that
This
your-
is not divine notation, that's to give you the feel goods.
Yeah. Is that your discrete topology?
This is exactly how I would have defined it to you in discrete math. Oh, is that the discrete topology? Yes.
Okay.
Same thing. Good?
Yep.
Next one, A cross B.
Wait. Okay, sorry. No, I have a question. Why does it have to be an axiom? Why can't that be a theorem?
Why can't that be a theorem? So, it almost feels like we should be able to construct the power set of a set. I'd have to play with it to see if there's somehow that we get in trouble. My intuition is when the set is finite, then we should be able to do it with what's given. That's my intuition. But we're going to have an axiom that tells us there's such thing as an infinite set. In fact, it's axiom 7. And so once we get axiom 7, an infinite set, this tells us that, and that infinite set has a power set, which I don't think we could have constructed. That is my gut. It could be wrong.
I see. Okay.
Okay. So now defining cross product of two sets. What is A cross B? Trying to show it to you the way you've most likely seen it before. That's a set of all ordered pairs A, B, where A, little a is in big A, and little b is in big B. Okay. Now let's define it precisely. Because we have to specify what set it comes from. And there has to be some set that it comes from.
Yep.
And so what is that set in the case of this? It is the power set of the union of the power set of the union of A and B. We were unioning that power set together with this A, all union together, put it inside a power set. And we're selecting from those things ordered pairs.
That in no way makes sense.
Yeah, power set of the
You have to sit there and play with it to figure out what the set is. It took me a couple minutes to figure out what the set is.
What is it?
That is the set of all the possible ordered pairs.
But it's like.
Well, it for sure has all the ordered pairs in it.
Oh, that's cool.
So I had to this took some thinking to come up with.
Oh, I see. Oh, okay. It's cool.
And there's no reason for you to sit there and say, oh, duh. The point is, you should say, what on earth is that monstrosity? And so while we should always write the set that we're selecting from, almost no one ever does, and everyone does it this way. And so these are the definitions you're going to see. Strictly speaking, they are not proper definitions. But nobody cares because giving these things proper definitions is a headache. We kind of make sure, hey, did we already make sure that this isn't breaking the rules? Someone did that? Okay, then this is the definition I'm going to use. And nobody actually goes and works with something like this directly.
But it's there.
We just validate, there was a way of doing this, and so we're okay doing this.
Yeah.
And so using this set builder notation, where we're not being careful, we often refer to it as naive set theory, where anything you do with set builder notation, we let fly. You kind of just have to know what you can and can't do. And most people don't go around breaking set theory when they just perform regular operations on it.
Yeah.
Okay. Define some of the operations we know and love. A union B is just a union of A and B together.
Yep.
But the way you know and love it is this definition, logically equivalent. What's A union B? It's a set of all x where x is in A or x is in B.
What is a union part of Axiom for?
Yes. But now I'm doing not union on a set, but union as a set operator.
Oh. Oh, okay.
As a binary operator.
Yep.
You can think about this as a unary operator. Now I'm defining the binary operator that you've most likely used 100 times.
Yep.
So here's its proper definition. Here's one that you're going to see outside this class anywhere you go.
Yep.
Similarly for intersection, here's its proper definition. Here's one you're going to see anywhere outside this class, everywhere you go. A intersect B is the set of all x where x is in A and x is in B. And we love these definitions because it exposes the logic so clearly of how to think about them.
But you're not defining a domain on where you're choosing the x's from.
Right. We are using what we call naive set theory. We're not going to be careful. But we know that this is okay because this is okay. And that's all it's doing. So here's our check that we're okay. And here's the way we really think about it. Because we're only selecting from sets, and so we're already safe. Let me write this to you, and you can see how stupid it is if I were to write it properly.
Okay.
Let me write it properly. What is A union B? Using set builder notation, it's a set of all x in the union on A and B, such that x is in A or x is in B.
So it's a recursive definition.
No, it's not. This is defined right here. Or sorry, this is defined all the way from Axiom 4.
Oh,
So forget this definition exists.
Yeah.
I can define it just like this, and now it is well defined, proper definition. But you see, it's the union. What do I mean by the union of A and B? Well, it's everything in the union, satisfying some condition that happens to get everything. So it's kind of stupid to write out the definition like that, where you already have that notion defined. But you could do that. Okay. And so now we get to one of the more interesting axioms. And again, we talked about this last week already, but there exists a set X that contains the empty set, and for every set Y in X, the set containing Y union with Y is also in X.
Oh, cool.
So to give intuition for this, I like to give an example of saying, I'm going to write out some secret set here. I'm going to tell you two things about this set. I'm going to tell you, one, the set A is a secret set. I'm going to tell you, one, that 0 is in A. And then I'm going to tell you that if K is in A, that implies K plus 1 is also in A.
Is addition here a well-defined operator?
This is just fill goods.
Okay.
So just for fill goods to give you intuition for what's going on here.
You wrote the same thing twice. Yeah, there you go.
Wait, wrong way.
K plus 1 is in A. Thank you. All right, so let's just think in this world for a second. So we're trying to figure out what's in A here. Now I already told you 0 is in A. So wherever A is, it has 0. Okay. Now I know for anything in A, that thing plus 1 is also in A.
That's through naturals.
So I know that 0 is in A. So 0 plus 1 is also in A.
So one's in A.
So 1's in A.
Which means
And now I know 1's in A. So 1 plus 1's in A, or in other words 2. And if 2's in A, 2 plus 1's in A, or 3. Or in 4. And 5. And yes, as you saw, that was just giving me the natural numbers.
So that gives you
So,
infinite sets.
yeah, it gives you an infinite set. So now what does this set contain? This set, over here, our secret set X, the empty set is in X. And if, what was the variable I used? Y. If Y is in X, that implies the set containing Y unioned with Y is also in X. So let's start out. What for sure is in X?
The empty set.
The empty set. The empty set is in X. Okay. Now, since I know that the empty set is in X, what else do I know is in set?
The empty set union with.
The set containing the empty set, union together with the empty set,
Which is the set containing the empty.
which is just the set containing the empty set.
No,
Isn't that just two sets inside?
no, it's not.
Let me get rid of empty set notation.
Okay, please do.
Oh, let me write it this way. The set containing the empty set, union together with the empty set. What's that equal to? I want everything that's in here or in here.
Set containing the empty set.
It's just a set containing the empty set.
Which is just
So
a
you already
set
have the
out of
second
the set.
containing set.
Now,
No, I'm not same thing.
so now I can now add the set containing the empty set. That is now something else I know is in here.
Oh. I got these now.
Do you keep going like that?
Yeah, so now let's repeat the process. So now I know that this is in there. So now I know that this is in there. I know the set containing that. Union together with that is also in there. When I take the unions of these two things, I got everything that's in the set, which is the set containing the empty set, together with the empty set.
That is not the empty set, that is the second containing the empty set.
That's the triple.
Everything that's in this set, which is the set containing the empty set,
Yeah.
together with everything in this set, which is the empty set.
That is. Oh, my bad.
That's an empty set symbol. Can you see that? Okay, sorry.
I can't, I gotta.
So we just really showed this is in there. Let me put big fat comma separations for our new elements. So now we just really showed that this is in there. Big fat comma. So we found another thing in there.
You forgot your bracket. You're missing. Oh, wait, did you?
I think I'm good.
Oh, you are.
That's all brackets.
You're right, you're right. Remember that.
And now what's the next thing in there? Well, this is going to get us in trouble thinking about this,
Why?
just because it blows up.
Oh. Well, let's do the next
So let's do one more, and then we'll call it good.
Okay.
So let's write one more element in here. It's the set containing this thing. So the set containing the empty set, together with the empty set.
No, you, wait.
Union, so now I'm just going to write the next element. Union, well, maybe that's a bad
You're
idea.
missing is squiggly.
You're right.
It is.
I was going to do it all in one go, but we'll write it down. I was just going to write out the union.
Okay.
But
Union.
Let's
with
write
the
this.
set containing the empty set.
union with whatever this was. So the set containing the empty set, together with the empty set. Right?
Yep.
So now let's carry out that union I'll write out here. That is the set containing this thing, the set containing the empty set, together with the empty set, and that set. So this set, I wrote right here, comma separate it. This is the next thing. Comma separate it.
Do you have all your brackets there?
Should.
He does.
So you see how this can quickly blow up, right?
Fascinating.
So when did we get to, what are we at, 3 now? Or
Yeah,
2?
we're at 3.
We're at 3. And we can go on our merry way, and we're not going to write the next one because it gets big. But here's what x is. Now, definitions. We define the empty set to be 0.
Okay.
We define 1 to be the set containing 0.
Okay.
We define 2 to be the set containing 1 and 0. We define 3 to be the set containing 2, 1, and 0.
Can we do that?
Yes.
Well, I mean, like, can we do that forever?
Yeah.
No, we need some kind of recursive definition.
Oh,
Oh,
now
yeah,
I
that's
see how.
A recursive definition, going through the numerals the way that you know the numerals.
So, is that like a well-defined thing that we can do?
Yep, this is completely well defined for any finite set.
So that, for any finite set,
Yes.
can we construct the entire natural numbers using that definition?
Yes. The natural numbers are the set of all finite ordinals. That's what the natural numbers are.
And that's exactly how we define it in logic too. The number system.
Yeah.
That's what we're in.
That we've already done
That
this
was,
process.
that was more.
Yeah, we did it last week.
I just think it's
but
awesome that
Reintroducing
it
it.
plugs in with.
So let me rewrite what x is equal to here.
That was just a good example.
The empty set
That's true.
is the same thing as 0. The set containing the empty set is the same thing as 1. The set containing 1 and 0
Oh, it's 2.
is 2.
Oh, that's sick.
The set containing 2, 1, and 0 is 3,
So 4 would
4,
actually be
5. 4 was this thing now. So writing out 4 because we weren't going to write it out. I didn't use any empty set symbols. I just actually wrote the empty brackets.
0, 1.
0, 1, 2, 3.
Six.
That can't be right because we have. Oh, wait. Okay, that's confusing to me.
Well, welcome to
I tried to create a heavy comma between each one.
The definition of
0, 1, 2, 3.
Hold on. The definition of 4 is 3 plus 1.
No, the definition.
No.
Or,
That's the definition of 4 in the axiomatic system of arithmetic. If we started with the axioms of arithmetic, you're right on the money. The point of set theory is we're going to start out with more foundational axioms. Axioms that you use in geometry, that you use in topology, that you use in all these different fields. And you can also construct arithmetic from it.
so why did you even bother with the axioms of arithmetic?
Because this is a lot of overhead for if you're just interested in arithmetic. And we'll just construct the same foundations anyways. So you don't get anything from doing all this. All this is validating that
It's possible.
set theory can give you those foundations.
If you
That's so confusing to me.
And so now you know anything you can prove in arithmetic, you could prove in set theory.
If you wanted to.
If you wanted to.
Wait, no, because you have axioms in arithmetic that you don't have in set theory.
Do we get anything in arithmetic that we don't get in set theory? I'd have to think about that.
Well, I don't know, because with Gödel's incompleteness theorem, I don't know.
Gödel's incompleteness theorem
'Cause he
is
goes
something
over-
that for sure can be generated from set theory.
Well, he needs it. You need it.
And so that means that you can get prime number, you can get the fundamental theory, the fundamental theorem of arithmetic you can get from ZFC set theory.
Yeah, you would have to be able to do arithmetic in set theory if it satisfies the incompleteness theorem. Because his theorem requires a system that is capable of doing arithmetic, doesn't it?
A lot of arithmetic. I don't know if there's something from arithmetic that we could skip. But I'd have to think about that. But yeah.
Computational theory covered that.
What did?
Computational theory covered all the way up to
Oh, no.
the incompleteness theorem. Is that what you call it?
We talked about the incompleteness theorem, but no, we went well beyond that in computation theory. That was just one of the interesting things we talked about.
But,
In
yeah.
computation theory, you get to really focus on what exactly is meant by things being decidable and undecidable.
But all you needed was a what do you call it? It's like a computer, but
Turing machine?
Turing machine. All you need is a Turing machine to prove the.
Incompleteness theorem?
The Turing machine cannot prove the incompleteness theorem.
Well, it's a computer that can't.
No. I don't know if that's what he's trying to say.
Yeah, I'm not saying it exactly right. But
All right.
anyways, I still don't understand why is 3 the definition of 3 the set 2 1
Containing.
0. Like, why does it matter? Why couldn't it?
We haven't defined plus.
Yeah, we haven't defined plus. You're right. So I can see how we can't use plus symbol in this situation. And why the heck are we deciding that 3 is 2 1 0?
Notice how many elements are in 3.
3.
Well, that okay.
Notice how many elements are in 2. How many elements are in 1? How many elements are in 0? How many elements are in 4?
So you're telling me
One of the nice properties about defining the numbers this way is the cardinality of every number is
Number?
a unique.
the number.
Well, it's a unique element. Is that what you're saying? The advantage here is.
He's saying that the cardinality of the set 4 is 4.
Well, it turns out defining the numbers this way is going to give us some nice properties.
Yeah.
We will try to hurry up and can give you, we won't construct the foundations of arithmetic, but I will try to give you enough feel-goods that you almost feel like you can see it if you squint. If you take off your glasses, you can see it. We'll try and reach that point of you feel like arithmetic's there. Because to get all the way, it's a lot, but. I'm going to define addition, multiplication, and lesson. Which if you remember when we did arithmetic, what were our undefined terms?
Addition.
0, 1, addition, multiplication,
And lesson.
and lesson.
So we would have to find all of our
And I will have defined subtraction. You can now define in terms of addition.
Because it's kind of like.
And so you can
intersection.
you can define subtraction identical in set theory to the way you already did in algebra.
Oh yeah. Okay, this all come back to me. Now I see exactly why we need it this way.
Okay. So now we have 0 defined and we have 1 defined. We have all the natural numbers defined, but we have all these things defined.
Okay.
Okay. So now, to continue our development of arithmetic, we have to introduce what's called the successor function. The successor function takes x, and it spits out
X
the set containing x union with x.
Isn't that what we were just doing in Axiom 7?
Yes, and when we were doing this right here, then if we had to find the successor function, I could have said if y is in x, then the successor of y is in x as well.
So that's
And we could rewrite this that way, and that would have been perfectly valid.
okay.
Good. So you see, intuitively, what does a successor function give you?
An extra element,
It gives you, it's like it's adding 1.
kind of. But yeah, I see it.
What is a successor of 2?
It's
The successor of 2
is the second page.
is equal to the set containing 2 union together with 2. What is 2? The set containing 1 and 0.
So it gives you 3.
So when you union that together, you get the set containing 0, 1, and 2, or in other words, 3. So a successor function, it's like a plus 1
It's
function.
an increment.
It's an incrementer.
Yeah.
You can think about it that way. And so we've encoded incrementing in terms of sets and the union operator that we've already defined.
Sweet.
Make sense?
Wait, are we gonna? I guess I'm jumping ahead a little bit, but how are we going to define negative numbers?
You can define negative numbers identical to the way that you define them in,
Arithmetic?
well, no, to define negative numbers, you have to use the integers. I'll give you a sense for how we get negatives. Because right now we just have the naturals. And again, I'm just going to give you a sense, unfortunately. Because we don't have equivalence classes, so I can't tell you precisely.
Do you need group theory for that?
No, equivalence classes, it would have been a topic of discrete math. It's just, it's a common thing that you do.
Is it like more fundamental?
If we continued this for 3 more classes, we would cover equivalence classes if I just kept building. So it's pretty foundational.
How much set theory is there?
I mean, there's a lot of places you could go and just keep building, and eventually you get to particular fields. It's not that unusual to do real analysis starting out with constructing the real numbers. That's not unusual.
Or topology?
Topology, you wouldn't construct the real numbers.
No, but we went straight from.
Oh, it's okay to start with this, but I mean actually go through the process of hurry up and give you the foundations and actually construct the real numbers, kind of like so far we've constructed the naturals. We can now say we've constructed the
construct
naturals.
all the real numbers purely opposite theory.
Yes.
Wait, what about that one axiom? Is it completeness axiom?
The completeness axiom you can get. What you can't get is the cardinality of the difference in cardinality between the real numbers and the naturals, and that has to be introduced as an axiom.
What?
Is there an infinite number of sets cardinalities between the naturals and the reals, or is the reals the next size after the naturals? And that has to be an axiom.
Why? Oh, whatever.
Anyways, getting arithmetic. We're giving you a taste for how we would define arithmetic.
Yeah.
So now that we have our successor function, we're ready to now define addition. So defining addition, and we have a recursive definition. M plus 0 is defined to be n. It's the first time we've seen that plus symbol. M plus, the successor of n, is a successor of m plus n.
Is that a valid definition?
Yes,
According to
this is a
theory?
valid recursive definition. So now, to show how this is well defined, it's graduate level math, but we get it, the fact that it's well defined, from Axiom 7 here, giving us infinity, and then from this Axiom 5 that we used, and setting up clever functions that makes that the outputs are still sets and we're okay.
Gotcha.
So it's not trivial showing how we derive it, but it is well defined.
Okay.
And so now, let's just manually write out some. Just going to compute some by hand.
Okay.
So let's start out by figuring out let's start with 2 plus 1. What's 2 plus 1? 2 plus 1 is equal to 2 plus,
The successor of 0.
perfect. This is equal to,
Successor of. Wait, how does that work?
keep going, you'll see it, it'll come out to you. Just blindly follow it. Where's it taking you?
Successor of 2 plus 0.
What's 2 plus 0 equal to?
Oh. 2.
So it's a successor of 2, and what's a successor of 2?
3.
You just flat out go through a successor function, that spits out 3. And so 2 plus 1 is in fact equal to 3.
Okay, so let's do something like 2 plus 2.
Yeah, so 2 plus 2 is a wonderful place to go next. I don't want to go off my board here. So 2 plus 2 is equal to 2 plus the successor of 1, which is equal to the successor of 2 plus 1. 2 plus 1, we just barely calculated. It's 3. So this is equal to the successor of 3, which is equal to 4. And now we could do 2 plus 3, and 2 plus 4, and 2 plus 5. And so it builds from the bottom up.
Seems like almost unnecessary to have to mention a successor.
No, it doesn't.
Now everything's defined in terms of the successor function. And now we can do multiplication. By definition, m times 0 is 0.
Okay.
And now, m times the successor of n is m times n plus n.
Oh.
So let's manually calculate one of those.
Okay.
So let's do 3 times 0, we already know is 0. So let's do 3 times 1. What is that equal to by definition?
3 times the successor of 0.
3 times the successor of 0, which is equal to, just blindly fall through there.
3 times 0 plus 3.
3 times 0 is
0.
0. And then 0 plus 3 is something that's defined from up here as being 3.
This is like magic. Okay, let's do like 3 times 3 then.
Okay, but understand that 3 times 3 would be dependent upon 3 times 2 for its definition, because it's recursive. So we have to know what 3 times 2 is before we define 3 times 3.
Okay.
The same way that you can't know what 3 is without first knowing what 2 is.
This is trippy.
Okay.
The point of this is not, no one performs arithmetic this way. The point is to prove that arithmetic can be performed this way. So keep in mind that this is not meant to be some elegant way of making this computation. It's just simply trying to prove to you that set theory can indeed construct arithmetic. So, I mean, I think it's worthwhile trying to force your brain to wrap around with this stuff, but just keep that in mind, what the point of the exercise is. All right, so now we were going to do 3 times 3, and we're going to assume that we already know 3 times 2 is 6.
Yeah.
And so we'll perform now 3 times 3.
I almost wish I could see this in set raw form.
Oh, you don't. It would be like reading binary. This is like the binary of mathematics.
It is kind of like it.
Yeah, it kind of is.
And no one on God's green earth wants to read binary.
Well, I like to think, study single 8-bit,
Yeah, but it's pretty brutal.
There are some use cases, for academic purposes. You're trying to learn, okay, how exactly does an adder work or whatever. And,
Yeah.
But outside of that, or I guess assembly language, did a bit with assembly language, learning which bit where does exactly what process, and that can be useful, but
Binary is pain.
hard to find a lot of applications for.
Honestly, I was going to think that plus and times and whatnot were going to coincide more with the power set, or the power set, or the intersection, or the union.
Notice that they do very much correspond with the union.
They do, that's right. But all
They
of them
do.
apparently. Or at least
Both
times
addition and
class.
multiplication are very closely tied with union.
Fair enough.
Okay, so 3 times 3 is, just blindly going through it without even thinking about it, 3 times the successor of 2, which is equal to, what is it? And if we had carried out 3 times 2 first, we would have found out that it was equal to 3 plus 3, which is 6.
That does not feel like it should work.
So, assuming that we already knew that 3 times 2 was 6, we would have had to do that first. And doing arithmetic, since this is defined first, 3 plus 3 is already defined. And so we know 3 plus 3 is 6.
It's very strange.
See it?
Yeah.
So, it works. And it works. It gives us all the things that we know and love. Now, here's the most beautiful of them, in my little opinion. Defining the less than operator. What does it mean to say m is less than n? Easy. M is in n.
Triple sets.
Oh, that's awesome.
Everything's
Everything's
sense.
that. I bet.
So, notice that is 1 1 is less than 7,
Oh,
so that's the
that's
same
so
thing as
cool.
1 is in 7.
That's so cool.
But what is 7? 7, if we were to write it out, not all the insanity, but somewhat sanity, it's 0, 1, 2, 3, 4, 5, 6.
Nice.
And so 1 is in 7. And that's what less than means. And so this membership
Whoa.
relation, it orders things for us. It gives us order.
Yeah. I feel like I can't even look at numbers the same way you did.
Wonderful, isn't it? There's so much more to these numbers than you ever thought. And that's why you would love number theory a lot more than you think.
Amazing the way you taught it. The way I took it online in class sucked.
I believe it. Okay. Now, defining the negative numbers, the integers. How do we define the integers? And I say, kinda. We have to use something called equivalence classes, which we don't have, so just ish.
N cross N.
N cross N, I'll give you the idea. N cross N is a set of all ordered pairs of naturals, right?
Yep.
And so if I take the ordered pair, something like 1, 4, that actually encodes -3. It encodes the difference between the two. You do the first minus the second, and that's what it encodes. And so you'll notice that there's actually an infinite number of ways to write -3, which is why you need something called equivalence classes. But notice that with an ordered pair, I could communicate to you any integer. If I say, here's our agreement, you're always going to do this one minus that one, that's the integer I mean.
But we
You could tell me any integer you want, and I could write it for you.
haven't defined subtraction yet.
No, it's, again, I said I'm just going to give you the feel-goods for how we can do it. And not actually get all these things well defined. I'm just trying to get you to see how you could encode all integers as ordered pairs of naturals.
Yeah.
And now you tell me any integer to write, and I could write it. What's 100? Any positive integer is simple. And then any negative integer, the way that everyone actually writes it, is if you told me to write -100. Here's the way everyone would have actually written it. But it turns out there's an infinite number of ways to write both of them.
We'll just define it that way.
Working with equivalence classes are nice.
Okay.
So it's not a big deal using equivalence class, you're just not used to it. And so it's actually a pretty clean way rather than trying to restrict which element exactly we're going to use. And then similarly, now we can think about the rationals as being cross product of integers. You think about a rational as just an integer over an integer.
Did I give you a quadruplet? Or am I thinking about that wrong? Because the integers are just.
Integers are ordered pairs, but who cares?
So what's an order?
They're sets of stuff. And so now this is just a set of integers. Who cares what an integer is? It's just an integer. Remember, it's all just sets when it's all said and done.
Yeah.
So now notice that you could encode every rational as an ordered pair of integers. And so if you said do something like -5/3, that would be -5, 3. Again, just giving you the feel goods for it. We're not rigorously defining these things. I'm jumping way ahead. And then here's a crazy one, and I will give you no intuition for this.
Come on.
We define the reals then to be the power set on the naturals.
How does that work?
That makes sense.
Makes sense to one of us, at least appealing to the intuition. Constructing the reals is a couple week exercise itself.
Couple weeks.
Probably.
That's because the reals are kind of like the natural squared.
Not like the natural squared. The natural squared is like the integers.
Yeah.
Think about this. Taking infinity and squaring it, it doesn't really change its size.
No.
Raising infinity to the power of 4 doesn't really change its size. Take the power set of infinity, and you got a whole new infinity.
Natural times 2 is the integer. Or
No.
integers times 2 is the
Oh, here's what I bet you're thinking of. Which, yes.
That makes sense.
And this is another way that there's no reason for you to know why, that we often write the power set.
What?
2 to the power, 2 to the naturals.
Yeah. I didn't even know you did that.
Oh, wow.
Yes, you can write it that way.
That is... Okay, so it's like infinity, 2 to the infinity.
So
Like 2 to the infinity now gets us a new infinity.
I guess like kind of.
But just taking infinities and adding them together or multiplying them by each other doesn't do
So let's
nothing.
take a real number. Okay, can we take a real number and write it in terms of natural?
No.
Oh. Then that's not a subset of natural numbers then. So how does that definition make sense? If you can't write a real number as a set of natural numbers, then how can it be defined as a power set of natural numbers?
So let me show you something in the power set of the natural numbers.
Okay.
Because every number can be in.
Write that for me, please.
Okay. Well, let's take something.
Now do it again, but this time don't include the number 2. Now do it again, this time don't include the number 2, 5, 17, and 1,885,265,000 other random naturals I decide to exclude. This is a beast.
And that corresponds to one real number.
No, the real numbers, sorry.
Oh, well, right,
But let me help your intuition here. Intuitively, what is a real number? It's an infinite decimal expansion.
yeah.
Yeah,
Okay.
Okay, so for every integer, you can have another infinite decimal expansion for each integer.
Well, that was for talking about the reals. For the naturals, we don't, or for the integers, we don't need to do anything crazy. They are much simpler to talk
Can you
about.
take a real number and show me what it looks like in terms of a set of natural numbers? No, you can't.
No, we'd have to talk about something called Dedekind cuts.
How on
It's a topic.
earth did anybody come to that definition?
Not starting with it, working backwards to it.
It's true.
Set theory, they did not start with the axioms.
They figured
They-
this out later.
Very smart people sit here and they work backwards and they fiddle with these things, fiddle with these things, fiddle with these things, and they start saying, oh my goodness. Is there even a difference between how we use this here and how we use that in arithmetic? And they go on their merry way. Okay. Yep. We gotta finish. So, we only have 2 more axioms to talk about. Definition really quick. X and Y are disjoint if and only if their intersection is the empty set.
Right.
Meaning they don't have any elements in common. So we already did an example of that somewhere.
Yeah, we did it.
Over here. This set and this set, these are disjoint sets because their intersection is the empty set.
Yep.
So, and then a collection of sets M is mutually disjoint if for any 2 sets in M, as long as you pick 2 different sets, you don't get to pick the same set twice. Pick any 2 sets out of M you want. If their intersection is empty, we say the sets are mutually disjoint. In other words, if on a school day, you have all the students in the different classrooms. Those classrooms are mutually disjoint. Each student shows up in only one of those classrooms. I never have a student showing up in 2 classrooms. So the classrooms would be disjoint sets.
Good.
Okay. Axiom 8. Every non-empty set contains at least one element y, such that x intersected with y is the empty set. Every non-empty set x contains at least one element y, such that x intersected with y is the empty set. Every set contains an element, such that if you intersect the set with its own element, you get the empty set. Intuitively, what this prevents is stuff like this. X being equal to the set containing x.
But what
This
about-
is impossible because we have x. There's only one element in there. When we intersect x with one of its elements in there, we don't get the empty set. There has to be an element in there such that when we intersect x with it, we don't get the empty set.
But what about the power set? Doesn't.
The power set does not contain itself. The power set of the set containing 1, 2 is equal to the set containing set 1, 2. Set containing 1, set containing 2, and the empty set. This whole thing is a power set. This whole thing doesn't show up in here. Okay, and then finally the last one, one of the more interesting ones, the last one to be added. This one's called the axiom of choice, pretty famous one.
Pretty cool.
Let M be a collection of non-empty and mutually disjoint sets. Then there exists a set X that contains exactly one element from each set in M. So try and draw this as a picture. M is equal to some set of sets. Let me draw the sets as just circle blobs. So all those things, all these things, all these things, all these things. Now, if something shows up in here, it does not show up in any of these other sets. They're mutually disjoint. So what we're saying is there exists some set X in existence such that I can pick one thing out of there and stick it right here. I can take little a from here, stick it right there. I can take little b from here, stick it right there. I can take little c from here, stick it right there. I can take little d from here, stick it right there.
Is this what allows your diagonals and hebrews? Or this gives you a
This, intuitively, what this gives us is a way of ordering
the infinities?
in infinite sets. I don't know if I can explain that on the fly.
That gives you well ordering for your infinite
So, yeah, so think about trying to order the real numbers. How do you put the real, let's first think about ordering the naturals.
Okay.
It's real easy to order the naturals. We'll just go 0, 1, 2, 3, 4, dot, dot, dot. Okay, that was easy. Let's try and order the integers. Where do you start? If we start negative 100, and start counting forward, negative 99, negative 98,
You start at 0.
then we don't really get them all.
No, you don't start at 0. You do like the dot 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 both ways. You have
But we got to order it. So which one comes first?
It's 0 going back and 0 going forward.
You can.
And you can order the integers, we just have to be a little bit clever with it. I could do 0, 1, negative 1, 2,
Oh, that's right.
negative 2,
Yeah.
3, negative 3. There we go. They're ordered, something comes first, and I'll eventually list out all the integers.
Eventually.
Fair enough.
Now the rationals we can also order. It's a little bit harder to see how. You have to use a method called dovetailing. We actually did it in computation theory.
Yeah, I remember.
But you can order the rationals, and there's a way to do it. Ordering the reals is much harder. How on earth do you order the reals?
Well, there's an infinite amount.
Even when you pick some real number to start with, say for some reason you want to start with 1.67, whatever, what comes next? What's the number that comes after 1.67? To give you a sense for how we order the rationals, because that would probably help, we start with basically 0, and then we do 1 over 1, and then negative 1 over 1. And then we do 1 over 2, negative 1 over 2, 2 over 1, negative 2 over 1. And then with all the ways you can do it with 3's and 2's and 1's. And then 4's and 3's and 2's and 1's. And then 5's and 4's and 3's and 2's and 1's. And that's how you can do the rationals.
Gotcha.
So how can we order the reals? Like what comes next?
No, but it doesn't really feel like anything does. Because you have an infinite
things
amount.
do come next.
You have an infinite amount.
What
of
do you put
rationals.
next? What comes after 1.67?
1.68.
Is it 1.68? What about 1.671?
I don't see how you could. Well, I know you can, but like.
So how do you order the real numbers?
Uh.
And so, yeah, famous mathematicians spent lots of their time trying to think about how to order the real numbers. And it turns out this axiom of choice enables you to order the real numbers. Here's the kicker. You don't know what the order is, you just know that they can be ordered. It's one of those things where it guarantees you that you can order them. It doesn't tell you what the order is.
So what's
haven't
the
figured
guarantee
it out
order?
yet.
How do you get that?
Because the axiom of choice, I can't tell you how we order them, we're already running out of time. But the axiom of choice just tells you that you can take something out of there, can take something out of there, can take something out of there, can take something out of there. And start making some collection of those things. But it never tells you which element you choose out of there. And so the way to do it, here's a way to think about it. I'm going to pick some random element out of here. I'll try and give you a sense for it without being too rigorous. I pick some random thing out of there. We'll call it a sub 1. Here's some infinite set. The axiom of choice says that I can select some element out of there. Okay. Now, for my next set, I pick the real numbers minus a. So it has everything except that a in there.
Wait, they're all the same?
And now, we'll call that a1. So it has everything but a1 in there. And I pick some random element out of there. And now that's going to be a sub 2, is what I pick out of there. And then get rid of a1 and a sub 2. a1, a sub 2, a sub 3. And so there's infinitely number of these sets. The axiom of choice enables me to select from an infinite number of sets, one element from each thing.
Why is it called the axiom of choice?
Because it enables us to choose one thing out of some infinite set. So it enables us to choose when there's no good way for saying what you want to pick from a set.
Oh, I see how.
Imagine that you have an infinite number of sets and you want to say how you're going to pick an element out of there. There's not always a good way to say the element that you pick out of there. You might say, I want to pick the smallest thing out of there. What if the set you're talking about was an open interval 0 to 1? There is no smallest thing in there.
Yeah.
So when you have these number of sets, and there is no good way for saying how you want to select something from it, and you don't really even know what exactly are in that set to select, you can't come up with a procedure to select it. There's no good way of knowing what's in the set. The axiom of choice still guarantees you can grab something out of there.
That seems pretty important.
It is important, yes. It's important in more advanced math. The only time you've probably ever explicitly needed this relied on was a proof using basis elements. Is about the only time it actually comes up.
That would make sense.
Outside of that, I haven't had to come across it. So I told you we are doing what is called ZFC set theory. Z and F are just initials for the two guys who developed it.
Which are?
I don't know. They're weird names.
Fair enough.
The C here means the axiom of choice, C for choice. And so there is ZF set theory, and then there's ZFC set theory, which is set theory without including this axiom, and set theory with including the axiom. A lot of people did not like this early on, but now it's almost a norm to always use ZFC set theory. But initially, I mean, when they did it, it was without the axiom of choice. It was something that came later. And then people decided to do it. Because there's still reasons that people don't like this. The axiom of choice also enables you to do some really strange things.
Oh yeah, I've seen some stuff like that. Like you can like duplicate spheres and stuff.
You can duplicate surface areas, so yes, a sphere. You can duplicate lengths, you can duplicate surface areas, technically only using the same things that you had. It almost feels like topology with it. And the sets you have to work with are sets that are, in some sense, not measurable. And yet you're using sets that aren't measurable and combining them in ways that they give you something. It's kind of intuitively like thinking about with an integral, the area under just that point is nothing, and the area under just this point is nothing, and yet when we do the area under all infinitely many of those points, now we get an area. And so we get all these zeros, 0, 0, 0, 0, 0, but you add up enough zeros and you get a number. The number comes out to 2.67 or whatever it is. It's a similar idea, but not the same idea. Okay, so there you go. There's your taste for set theory, for ZFC set theory. That's where we're going to end logic.
Does this go on? How much more set theory is there that we haven't covered?
I don't know how to answer that question because set theory goes to all sorts of things. There are going to be graduate level set theory courses that do way more than this. And there's tons that you can still do. Like if we were continuing with real analysis, I would probably keep going and constructing the real numbers. That's why I'm saying real analysis would have been a very natural one to continue after this course. But you guys chose history, so we'll do that.
We didn't choose history.
They chose history.
People did. Yeah, should we only count the people that showed up? Or stayed till the end?
Maybe the people who
Stayed only get 2 votes.
Yeah.
To vote on the next one.
I probably should have given you guys 2 votes. Any questions for what we're recording here? All right, cool. Another class under our belts.